Hello, today we are going to discuss about Felkin Anh model. It is very important model which is used to predict the major product in a nucleophilic addition reaction to a carbonyl compound having alpha chiral center. Okay, this is the general mechanism. This is our nucleophile. So this nucleophile can approach this carbonyl compound either through upward or backward. If it is approaching through the upward, what will happen? Nucleophile comes in wedge and OH comes dash. If nucleophile approaching below the plane of paper, what will happen? Nucleophile comes below the plane, OH comes to above the plane. Okay, so these two are related as diastereomers. So this model is used to predict among these which one is the major product. So that is the charm of this model. We can predict the major product among these two diastereomers. That's why it is called diastereoselective asymmetric induction. Moreover, in this reaction we can have no chiral center. That's why it is called 1-2 asymmetric induction. And the main thing is that this Felkin Anh model is applicable only your reagent is free from lithium, zinc, magnesium, copper, titanium, cerium, manganese. If these reagents are present, our selectivity is somewhat different. That is called chelate model that we will discuss later. Now we can go deeply by taking an example. So this is our example. So this is our carbonyl compound. So this is our alpha chiral center having a phenyl substituent that is in the plane of paper and Me that is in wedge H in dash. So this chiral center, this alpha chiral center is classified accordingly their size. So the substituent in this chiral center classified into large, medium, small. Okay, so here we are using a lithium aluminum hydride. We know that that is a reducing agent that will furnish H- ion as a nucleophile. So in this model, the first step is that conversion of the given flying wedge into Newman projection. That is very important. So in order to convert, we are going to take our carbonyl carbon center as a front carbon and alpha carbon as a back carbon. So when we are moving to its Newman projection, our carbonyl carbon, when we are viewing this position, carbonyl carbon like this, and we know that that is coplanar with that is carbonyl carbon. So the front carbon like this. And our back carbon, that is our alpha carbon. So we know that pH is coplanar with CO, carbonyl compound. So that becomes just backside of carbonyl carbon. Now we have two substituent at alpha carbon, Me in wedge, H in dash. When you are observing from this side, okay, so your left hand side possess Me, your right hand side possess hydrogen. That same reflect in this. So left hand side possess Me, right hand side possess hydrogen. Now we want to convert this into Felkin Anh model. So the Felkin Anh model says that in your compound, the larger group possessed in alpha carbon should be perpendicular with respect to the carbonyl compound. So our alpha carbon having pH H Me. Among this, we know that pH is larger group. So accordingly, pH should be perpendicular with respect to carbonyl compound. So our larger group, that is perpendicular to carbonyl compound. We can have another possibility also. When I am rotating this towards left, what will happen? pH comes this position. It is also perpendicular with respect to carbonyl. These two are Felkin Anh model. So I repeat, in Felkin Anh model, we want to convert in such a manner larger group possessing alpha carbon should be perpendicular with respect to the carbonyl compound. Okay. So these two are our Felkin Anh model. Now we want to take one of these in such a manner. They are attributing that nucleophile approach takes place in such a manner your bond angle between smallest substituent and carbonyl compound should be greater than or equal to 107. So in this situation, our alpha carbon having hydrogen, that is smallest group. So this is our bond angle. We know that it is greater than or equal to 107. But in this situation, that is less than 107. So in order to approach nucleophile, the angle between smallest group and carbonyl group should be greater than or equal to 107. That angle is called Brugge-Dunitz angle. Okay, so this is the preferred conformation. So the nucleophilic attack from less hindered site having Brugge-Dunitz angle 107. So we have taken this as our preferred conformation. Now what will happen? This is our reagent, lithium aluminum hydrate, that will furnish H- as a nucleophile. So accordingly, this H- approach to the carbonyl center through the smallest group present in alpha carbon having bond angle 107. Okay, so this is our nucleophile. So what will happen? This is our situation. So nucleophile attack, shift. Okay, so this bond gets shifted. So this is the situation. There is no change in the back carbon, MEHPH. Now this is our incoming nucleophile hydrogen bond O minus ET. Now on protonation we will end up with this structure. This is our product. But we want to obtain this product in flying wedge. That is very important. So how can we convert this preferred flying wedge structure? So this is our product. The main thing is that before converting this into flying wedge, we want to analyze our starting material. What are the species in the plane of paper? Okay, what are the species in wedge or dash at alpha carbon? That should be remember. So we want to analyze our starting material. This is our starting material. We know pH in the alpha carbon in the plane of paper, ET group at the carbonyl carbon in the plane of paper, and Me group wedge, that is above the plane of paper, H below the plane of paper. So those things should be reflected in the product also. That is mandatory. So suppose if you have an objective question, so we want to obtain answer in accordingly given options. So what are the species present at the plane of paper, what are the species present at wedge or dash at the alpha carbon? Okay, so in order to make that way, I want to place pH and ET coplanar. Okay, coplanar. Here ET and Me, they are not at all coplanar. So I want to convert they in coplanar. Coplanar means we know that in the plane of paper they are in the same plane. Okay, they are in the same plane. That's why I mentioned coplanar. Okay. So in order to, so here ET and Me are coplanar. So in order to make ET and pH coplanar, we want to rotate this back carbon to 120 degree. After rotating, I can have this structure. I can have this structure. Now your ET and pH are coplanar. So that means they are in the plane of paper. So pH bond front carbon ET, they are in the plane of paper. Now we have 4 substituent. 2 are in the same side, other 2 are in the same side. Okay. Now another procedure is that whatever the species present in the alpha carbon, we want to retain their stereochemistry in the product also. That is very important. We know that in the starting material, we know that Me in wedge, H in dash, that should be reflected in product. Me wedge means that they are in the above plane. Okay, so when we are analyzing the group present at alpha carbon, should be retain their stereochemistry. In order to retain their stereochemistry, we want to observe from that side, that is Me is wedge, so we want to observe the position of Me. So we know that Me is here. This is our alpha carbon, back carbon, so Me is here. So we want to observe this molecule from this side. So when we are observing that side, that implies those group present at that position comes wedge. I repeat, if we are observing from where we are observing, the group present at that side should be retained in wedge, and the group present other side should be retained in dash. Okay, ready. So for clarity, I wrote in different color, pH and ET in red. So pH, ET, they are in red, they are in the plane of paper, so pH here, ET here. Okay, now Me that is present in back carbon, that is alpha carbon, that should be in wedge. Ready. And H present at front carbon, that should be in wedge. Okay, so Me in back carbon should be in wedge, H in front carbon should be in wedge. Why? Because we are observing from that side. Then OH in the front carbon, that should be in dash, because that is the position opposite to our observation. OH in dash, H in below the back carbon should be in dash. Clear? So pH, H in the plane of paper, black color front H in dash, wedge, black color Me in wedge, blue color OH in the front carbon dash, blue color OH in the back carbon in dash. So according to Felkin Anh model, this is our major product. We can have another option also. In next option, our alpha carbon stereochemistry should be retained. The stereochemistry change at our carbonyl carbon only. Here H in wedge, OH in dash, H in wedge, OH in dash. Here OH in wedge, H in dash. Stereochemistry just changed. This implies our nucleophilic hydrogen wedge, that means nucleophile attack takes place in the above plane of paper. Here nucleophilic hydrogen in dash, that means nucleophilic attack takes place below the plane of paper. In accordance with the Felkin Anh model, this is our major product. That means in this given compound, the nucleophilic attack is favorable via above the plane of paper. Okay, clear? So if you are thinking this is very important, please like, share and subscribe. Thank you. Take care.